All right. Okay. So we were looking at knife-based classification last time, right? So today what we are going to do is we are going to work through an example to see how the algorithm works. All right. If you refer to the notes, we have an algorithm there. Here, this is essentially an algorithm for knife-based classification. However, this is one type of knife-based classifier, which is using MLE estimates, okay, the maximum likelihood estimates. But you can convert them into other types of classifiers as well. So, for example, if you want to incorporate the prior, then you can convert these probabilities into slightly different probabilities. So, if you remember from 2 classes back, right, when we were trying to learn the parameters of a Bernoulli distribution, we came to things like these. We saw things like these if we were doing maximum likelihood estimation, right? However, if you want to incorporate a prior, then those numbers, those expressions change. So, for example, if you wanted to do something like a Bayesian averaging, then instead of n over n1 over n, you would add this, right? If you remember, if you were doing MAP, which is maximum a priori classification, ooh, this is all over the place. Here, then you could use, yeah, then you could pretty much use n1 over n1 plus a0 minus 1 over something. I'll come to that. So these notes, okay. But what we are going to do today is just sort of go through the algorithm via an example, and I've seen that that sort of works better. All right. So let's do that. Go here. Okay. So I'll leave this data set up here. So let's first look at this data set, right? So here you have a data set in which you have some x's. Each input is a 3-dimensional vector, right? So each attribute, there are 3 attributes. One is shape, size, and color. Each one of them is binary. It can take 2 values, circular or oval, large or small, light or dark. And we have to predict the type. So this is the class. There could be 2 types of classes, malignant or benign, right? Now, since all of these are binary, right, which means that we can individually model them as Bernoulli distributions, which is coin tosses, right? However, if you remember our discussion on classifiers, right? So what we want is the probability of, so if I give you a new test example which looks like this, I want to find what is the probability of y, which is the output, to be malignant given x is x star. Given x is this, right? And then probability of y equal to benign, given x is x star, and then whichever is higher, that's the predicted class, right? Now, by Bayes' rule, you can compute this as probability of x equal to x star given y is malignant. So that is the class conditional probability times probability of y to be malignant without seeing any data. So that's the prior on y divided by a summation which essentially does both. Malignant times py equal to malignant plus px equal to x star y is equal to benign times py equal to benign, right? So this is, we have been looking at this many times last 2 weeks. Right? Any questions about that part? All right. So now comes the question that what are these things? So let's first focus on this, right? This you can estimate, you can model the random variable y as a Bernoulli distribution, which means that to compute this, you want the probability of, you want some theta malignant, right? You want to learn the parameters of this coin, right? And this essentially will be y equal to malignant. And same way you can compute probability of y is equal to benign, which is theta benign, and these, they have to sum up to 1. So even if you just compute this, that will be fine, right? So that is one thing that you want to compute, and that you can easily compute, right? So for example, if you are doing a maximum likelihood estimate, right? So what would this be? So since here we are not dealing with your training data at all, so we can hide this. We can say, okay, forget about the examples, right? All we have are these observations. So think of this exactly like your coin toss. Yeah. So in coin tossing, what we did two classes back was we said, okay, we just know what the output of the coin tosses were. So think of malignant as, let's say, H, heads, heads, tails, heads, tails, heads, tails, heads, tails, tails, heads, right? So now we know how to compute this, right? That's the MLE, right? So can anyone tell what is theta m going to be? Theta m by MLE estimate. It's 1 over 2, right? 5 by 10. So because theta MLE is just number of heads that we see divided by total number of tosses, or number of times we saw malignant divided by total number of tosses, which is 5 by 10. So that's 0.5. Right? So now we have computed this, right? Now you could make it even more interesting if you want to say incorporate some prior. If somebody says, hey, can you, because we want to avoid things like the black swan paradox, right? So let's say if somebody says, you know, the prior on theta m is a beta distribution with some a0, b0 as the parameters of that beta distribution, then instead of using this, what you would do is you would use, you could use the map, which would be nm plus a0 minus 1 over n plus a0 plus b0 minus 1, right? Or minus 2, I think. So that is, I mean, if you refer to the notes, that's the exact expression, right? Someone could say, instead of doing this, could you do the Bayesian averaging, right? So we can do that as well. In that case, the Bayesian averaging would just be nm plus a0 over n plus a0 plus b0. All right. So these are the different estimates that you can get for theta. Okay. So that's fine. Now the next question becomes, how do you compute this, right? And this is where things become more interesting. So okay. How to compute the class conditional, right? Star y is equal to malignant. Now remember that this x is not just one random variable, it's a vector of 3 random variables, right? So which means that if you want to compute a full probability distribution, we saw that in last class, we would need 2 to the power 3 minus 1 probabilities, right? Because you would want to, so what is a probability distribution, right? Probability distribution is essentially enumeration of all probabilities of all combinations, right? So a probability distribution for this would be, what is the probability of x to be, you know, circular large light given y is equal to malignant? What is probability of x to be circular large dark, y is equal to malignant, and so on, right? So you need to compute all of these, which means that you need, because you could have 2 power d, 2 power 3 combinations like these, but the last one would just be 1 minus sum of previous, right? So we typically say that there will be 2 power 3 minus 1, or 7 parameters that you need for this distribution, right? Which are too many, especially if d becomes very large, you do not want to maintain so many of them, right? The other point is that even estimating these, right? How would you estimate these? What you would do is you will go to your data set, right? And then you will say, okay, how many times did I see this combination for malignant, right? Circular large light, yeah? Now what will happen is that if you have too many combinations, you will need a lot of data to have to ensure that those combinations occur significant number of times, right? So that becomes an issue, because you need, especially when d becomes very large, when d becomes very large, this 2 power 3 becomes 2 power d, and you need a lot of data. So obviously we don't want to do that. So that's why we make what is called the naive Bayes assumption. What naive Bayes assumption says is it assumes that all of your these attributes are independent of each other. So which means that this joint distribution of x equal to circular large light given y equal to whatever becomes a product of individual probabilities. So x1 m times y equal to m times p x1 equal to light y equal to m, right? So suddenly you have simplified it a lot. So now we can see that now what is this, right? This is a probability distribution of a binary random variable which only needs one parameter, right? Because it can take only one value, or it can take only two values. One of them will be one minus of the other, right? So you just need one parameter here, plus one parameter here, plus one parameter here. So you just need three parameters. So instead of 7, you now need 3, right? In general, if you had d attributes, you would just need d parameters, right? So from 2 power d, suddenly you jump down to d. And also you need much lesser data. So that is why naive Bayes assumption sort of helps. Of course, it's not a free lunch, right? Because you are indeed making a very strong assumption. You are assuming that all of your attributes are independent of each other, which in reality would hardly happen, right? Because you can say, well, in this case, maybe it is. For this example, maybe you can assume that the shape, size, and color are independent of each other given the tumor. In reality, that might not happen, right? In reality, these things would be related, yeah, which means that the estimates that you would get from naive Bayes might not exactly be correct, because what you're saying is that the joint distribution of these things is just the product of this, but that might not be true, yeah. So don't think that naive Bayes is the answer to everything. In fact, that just by the name of naive, you can sense that it's not the best classifier, but in terms of efficiency, it's pretty good, right? Because you just need to compute d parameters for this. So now let us see how to compute these d parameters, right? So if you look at this now, sorry, if you look at this now, right, what you want to compute are these things. So what would be probability of x1, the first attribute, to be circular given y is equal to malignant, right? So if you think about this now, you can model this as a binary random variable or as a coin toss. So all you need to compute is what is the probability of this when class was this. So what would you do? What you do is you just consider those examples in which y is malignant, right? So this one, 1, 2, 3, 4, 5, and in that you essentially find out the theta for this coin, right? So all you do is you say, okay, when the malignant class circular, oval, circular. So out of 5, 3 times you saw circular, right? So if you're doing an MLE, this would just be 3 times 5, right? In general, you can write it as number of times you saw circular in the class malignant divided by number of times you saw class malignant, right? So that's what the algorithm would do. And now this is the MLE estimate, right? However, you can again employ a prior on this as well. So let's say you say, I'm going to employ a beta prior on this particular random variable, and I'm going to call it beta of A1 comma B1, right? So then you can use NCM plus A1 minus 1 over NM plus A1 plus B1 minus 2 if you want to use the map. Or you can say it is NCM plus A1 over NM plus A1 plus B1 if you want to use the Bayesian average, right? You have expressions for everything, all right? The algorithm that I have listed in the slides is only for MLE, right? So here we are only using the MLE estimates, but you can easily convert it into a Bayesian or a map estimate by adding the prior values, right? So fairly simple. Okay. So now let us see how to do it for this particular example. Any questions so far? All right. Okay. So just a reminder, the gradients problem that is there for this week, one of them essentially asks you to do this, right, for a different data set, but the procedure is the same. Okay, so this is the data, and let's say today we are going to look at MLE estimate. All right, so let us write out all of our probabilities. We have already written a few of them. So what we have done is that the prior probability, which is probability of Y to be malignant, is equal to theta MLE M is 0.5, because we see 5 out of 10, right? And the same thing, that the other one will be just 1 minus of this, but I'll just write it anyway, of benign is also 0.5. Right? Now we will do each of these possibilities, each of these attributes per class, right? So let's do it in two parts. So this one is for malignant and this one is benign. So we'll first say, what is the probability of x1 to be circular given y is malignant, right? And that one is computed by just counting all right, that one is computed by just saying, okay, let's look at the malignant examples and how many times did I see circular, right? So I did that earlier. I think it was 3 by 5. And then of course P x1 to be oval given y equal to malignant will be 2 by 5, right? Then we'll say, okay, what is the probability of x2 to be large given y equal to malignant? And that would be, let's say this is malignant, 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 malignant. So 4 out of 5 times we see that. And the probability of x2 to be small will be just 1 over 5. Right? Any questions so far? So I'm going to just do it just for the sake of thoroughness, and that will also help you solve similar problems later. X3 equal to light, y equal to malignant. So for that I just see when it's malignant, 1, 2, 3, 4, 5 out. So it's 1 and 2 out of 5 times you see light, and of course then the dark is equal to 3 by 5, right? And the same thing you can do for the benign case. Now you will look at the other things. So I'm not going to write these things. I'm just going to write the numbers. So for benign, if we are looking at, okay, let's write it. Circular y equal to benign, right? Now you are going to look at the benign rows and seeing how many times do I see circular. So 1 and 2. So it will be 2 by 5. And P x1 equal to oval given y equal to benign will be 3 by 5, right? And then same thing for large, 1, 2, 2 out of 5. And then small y equal to benign, 3 by 5. And then same thing goes here. So the light when it is benign, 1, 2, 3. So 3 by 5. And this would be of course 2 by 5. Any questions so far? All right. So this is essentially counting, right? Now, the way these things can become more complicated is, what if I say that this shape can take 3 values, right? The entire process is still the same, except that you will have to enumerate all probabilities, right? So let's say it was also circular, oval, and something irregular. Then you would have to compute x1 equal to circular, x1 equal to oval, and x1 equal to irregular, right? So that is how this would change. Naive Bayes would also work if your class type is also more than 2, right? The only thing that will change is now you'll have to enumerate all probabilities. So it will keep becoming complex and complex in terms of the number of things that you have to maintain, but the process is still the same, all right? So now let us see. So this is essentially the training part of Naive Bayes. You have done the training, okay? So let's call this the training. You know, for a small example, you can do it by hand, but it's very easy to implement as well. So now let's do the testing, right? So now if I ask you, what is the probability of y equal to malignant, right? Given x is this circular, small, and light. Okay? So remember this expression, right? So what you would have to do now is you have to say this probability is equal to, let me first write this. So y equal to malignant is of course 0.5. So that goes here times this. Now this is essentially, because we are making the Naive Bayes assumption, this becomes x1 equal to circular, x2 equal to small. So this x2 equal to small, this, and x3 equal to light, right? So it will be 3 by 5 times 1 by 5 times 2 by 5, right? Divided by the numerator, the denominator would have this plus, and then you would have things from the benign side, right? So you would have to put the theta benign, which would be 0.5 times the same thing. What is the probability of x to be circular given y benign? That's 2 by 5 times small with benign, 3 by 5 times light, 3 by 5. All right, and then you compute this thing, and this of course will be a probability because it is going to be between 0 and 1, and then you get that, right? So and the same way you can get the probability. You do not really have to compute y equal to benign. That will be just 1 minus of this, right? But if you have multiple classes, then you have to compute more of these. All right, any questions so far? It's fairly straightforward, right? After neural networks, you say, oh, wow. Yes? Right, very good question. So the question is this, that what if, right? What if, let's say just for the sake of example, right? Let's say this color took 3 values, light, dark, and medium. And let's say there was no medium here at all, or there was no medium for malignant, which means that the probability of x3 or x2, x3 to be medium given y equal to malignant would be 0, right? And then that would make these things 0, right? That will happen, right? So there is no way out of it. The way to handle things is by using the prior, right? Because this is the classic example of the black swan syndrome, which is if you've never seen a black swan, the probability of seeing a new black swan is 0 by maximum likelihood estimate. That is why we typically add, you know, when we have the prior, right, we add those values, right? So if you have a beta prior, what will happen is that even though the probability of x3 to be whatever medium given y equal to malignant is 0, the MLE, right? But you would not use that here. You know, when you're using a prior, you would be adding plus a 0 over something plus a. So even though this value is 0, you would have a non-zero value here. So that is the advantage of using the prior, right? Theta map or even the Bayesian averaging, there also you are adding a0 plus minus 1 on the top, right? So somehow you are, even though your observed numbers are 0, you would still be adding a constant over there, right? And what you would also see is that as your training data becomes larger, even if you are using a prior, right? So let's say you are using a prior on all of them. Let's say instead of this, you have 3 plus a0 over 5 plus a0 plus b0 if you're using Bayesian averaging, right? What will happen is that right now, this A0, this would have an impact on your probabilities. But as your data becomes very large, the effect of these would become very small because these numbers will become very large, right? So as the data grows, the impact of prior would go down. But in the beginning, the benefit of having a prior is because that will help you account for these fringe cases where you do not see any data at all. All right? Right, and that makes sense, right? Because in the beginning, what essentially this means is that when you have very less data, you haven't observed too much, then you want to rely on your prior a lot. But as you observe more and more and more, then you don't really care about your prior. You say, okay, let me use the data. Well, the choice doesn't go, I mean, that's not how it will happen, right? So you will decide beforehand, do I want to use the MLE or do I want to use the map, right? Or Bayesian average. So do I want to use a prior or not? That's the choice that you will make early on. So if you do not make the choice, then you would run into these kind of issues, right? So in general, in practice, you do want to make that choice. That's what I'm saying, because you do not want to run into these cases. But for these small examples, when I give you such problems for the gradients or for exams, right, there I would explicitly state that use this choice. Use the prior or do not use the prior. So then, even if it becomes 0, you would still have to go through that. Any other questions? Yes.
Why are domains using prior? Is it just because we're treating an unknown constant value as a random variable, or is there a deeper reason?
Okay, so the question is, why do frequentists don't want to use the prior? Well, I don't know, maybe I gave a wrong impression. So frequentists do use the prior. The only thing that they do not use is the Bayesian averaging way. So they typically tend to use the map estimates. So they would get the prior and they would multiply it with the likelihood and get the posterior. But then the hypothesis that they go with is the one with the highest posterior, not the Bayesian averaging, right? The reason they do that is because it's not against or for, but it's just two schools of thinking. So in frequentist approach, the parameters are not assumed as the random variables. And in the Bayesian approach, even the parameters are random variables. So that's the only difference. Yes and yeah, I mean, that's a way to explain it. But in the frequentist domain, they would still use the prior but not call it a prior on the probability. They would just say, these are the confidence I have on each value of the theta. So it's just sort of optics of how you see it. Right? But in general, for machine learning, I mean, machine learning algorithms, they tend to go the Bayesian way because that's how you could sort of stay in the probability space. Right. Actually, I'm not a big expert on these two schools, so but we can have a discussion later about this. Any other questions? All right. Okay. So this is fairly easy, right? Naive Bayes. You wish that you got this for your programming assignment, but okay. All right. So now let us go one step ahead, right? So we have looked at naive Bayes. So this ends our discussion. So the next question is, what happens? Oh. So the next question is that what happens if my attributes are continuous, okay? So for example, if I go back here, right? So in this example, each one of my attributes was taking 2 possible values. What if these are continuous? So let's say the size is actually a number that can go between -infinity and infinity. And the color is actually some gradient of the color, and the shape is, forget about the shape. So let's say they're all continuous, right? What happens then? The quick answer is that you can still apply naive Bayes, right? Because what naive Bayes asks for is that if you want to find the probabilities, all you need to know are these probabilities, right? So if your attribute value, if your attributes are not discrete, if they're not binary, then of course you cannot model them as a categorical distribution. You cannot model it as a Bernoulli distribution, but you can model it as something else, right? And then the naive Bayes assumption can still be applied and you can still work with it, right? So now we are going to look at what kind of distributions can you assume. So for example, you can assume that each variable is a univariate Gaussian distribution. All right. So remember, we had a quick discussion about Gaussian distributions, and I'm going to talk about it now. But essentially, you can still apply naive Bayes, but with a different distribution. So now let's talk about Gaussian random variables. Okay. So if you remember last class, I mentioned that I skipped a section in part 2 about Gaussian distributions. So we are going to come back to that. All right. So what is a Gaussian distribution? So Gaussian distribution is used to model random variables that can take any value between minus infinity and infinity. All right. The reason that distribution is so popular is because it happens a lot in nature. Okay. There is no real explanation for that, but if you look at a lot of natural processes, you will see they are oftentimes modeled as a Gaussian distribution. So, for example, if I if I take a sample of students, right, or any people, and I just ask for their ages, and I collect their ages, and then I plot a histogram, you will see more often than not that it will look like a Gaussian, right? It's a natural process, and that's why it looks like that, right? If you observe a lot of other things, so for example, even simple things like temperatures over many days and temperatures of different places, and just plot a empirical histogram out of that, you will see oftentimes it looks like a Gaussian, right? And that is why Gaussian distributions are so popular, because now you can assume that any random variable is modeled as a Gaussian distribution, and you won't be too far from the truth. In fact, I always there's a very interesting website that somebody forwarded it to me. So it was like this online, what do you call it? Like trivia website. It was called Sporco. Yeah. Oh yeah, it's there, right? So this is a website where you can play these trivia games, some random games. But the good part about this is that if you play it, right, and we won't play it, somewhere you could give up. Oh yeah, give up. So what this also shows is how did other folks do on this particular this website. They seem to have changed it. Quiz stats. All right. Maybe next time I'll show it to you. But what happens is that if you look at the numbers that come out, right, it often looks like a Gaussian. It's just miraculous. So when you essentially, so there are millions of people who have played a game, right, and that game had 20 possible scores that you could get. If you look at the distribution of those 20 scores, this website used to show that you would oftentimes see a Gaussian distribution. So it's a purely natural process, and somehow you always end up looking at a Gaussian distribution. So that's why this is just to motivate why Gaussian distributions are so popular. Distribution looks like. So of course, and we have seen that earlier as well. So this is the probability density function for a Gaussian distribution, right? A Gaussian distribution has two parameters. One is called mu and one is called sigma. And for any observation, the probability density at that point is given by this expression. So you want to remember this expression. This you will see everywhere, right? So it is essentially 1 over sigma under root 2 pi and exponential of this value. Yeah. So if you look at this distribution, this is how it looks like. So sorry. Somehow this. All right. So what I have done in this example is that I have sampled lot of points from a Gaussian distribution. So this is I created a Gaussian distribution in which I set my mu to 0 and sigma to 1. These are the two parameters. And then I generated 1000 samples out of that. All right. So if you look at the empirical distribution, if you look at how the histogram looks like, it looks like a bell shape. So that is a characteristic shape of a Gaussian distribution. All right. If you remember the beta distribution, right? So beta distribution, by choosing different parameters A and B, you could get different shapes, right? The difference between Gaussian and beta is that beta forced all your random variables to be between 0 and 1. This one goes all the way, yeah? But you can change these things. So let's say you make sigma to be 10. What will happen then is that your distribution becomes larger. Right. It becomes fatter. So sigma essentially controls the variance of your this bell curve, right? And what does mu do? Mu essentially sets where is the highest value, right? So right now mu is 0, so the biggest pole will be here. But if you move mu to 1, then your biggest pole will be around 1. So it will shift a little bit, right? So that is how the Gaussian distribution works, right? Then there is also this notion of multivariate Gaussian distribution, in which instead of having a small x, one value, you have a vector of values, right? So for example, you can create a, so the expression for the probability density is pretty much the same, right? So now your x is bold because it is a vector of d values. And then there are two parameters for this distribution as well. One is mu, which is now a vector, and uppercase sigma, which is a covariance matrix. All right, and then the expression for PDF looks like this. So it looks very much like the PDF for a one-dimensional one, except that now since x is no longer a vector or is no longer a scalar, so you express it like this. All right. So if you set your d to 1, then it will look exactly like the previous one. So for example, for d equal to 2, if your random variable has 2 entries, right? This looks like man, what's happening? I don't know what something I changed later. Right. So essentially these are different samples from this two-dimensional distribution. So each one has two attributes, x, x1 and x2, right? So by controlling the parameters mu and sigma, so remember now mu is a vector and sigma is a matrix, you can create these different things. So let's say I sample 10,000 points. This is how it will look, right? It will be centered at mu, and the sigma will control the shape of this ball, right? So for example, if I make my sigma like 10, 1, then it will become stretched, because what I'm essentially saying here is that the variance along the first one is more, along the second is smaller, right? Then you can also introduce these things. You can make the off diagonal values, and then it starts sort of rotating and everything. So it's a very interesting distribution, and it can be it can be generalized to any d. These are the examples that I'm showing you for d equal to 2, but you can generalize it for any large d as well, all right? So that is what Gaussian distribution is. So now going back to our naive base, now what we can do is we can model each one of your random variable as a univariate Gaussian if they are continuous, right? And then essentially the things that would change is that a little bit of your expression would change. Right. So now what will happen is that instead of having P of xj given y as a, just a theta for a Bernoulli distribution, now you would be looking at this kind of expression. All right. Any questions so far? All right. So what we will do next week is that we are going to look at this a little bit more, but then we will come up with new algorithms, which are essentially extensions of naive-based classifier for a for continuous case, and we call those quadratic discriminant analysis. All right, so we'll look at that on Monday, little bit on Wednesday. Maybe we will do a little bit of a review on Wednesday. So if you want to send me some questions from material that we have covered so far to discuss on Wednesday, just